Hello students, let us continue the discussion on units and measurements. As I said in the beginning, this chapter, the second chapter, units and measurements, basically has three parts in it: units, measurements, and dimensions. So far, whatever we have discussed has covered units and measurements. And this is the session where we are going to start dimensions. Okay. Now, what are dimensions? See, so far, when I say certain quantity, that quantity will have its own value, isn't it? If I say mass, 5 or 10, some numerical value will be there. Along with that, unit will also be associated with it. kg, 10 meter, 20 kilogram, like that, right? So they are the different. So when I say a quantity, it's the value, the numerical value, the unit, which are very important to express that quantity. Now, along with those two, the numerical value and the unit, we also have one more thing which is important to express the nature of that quantity, and that itself is the dimension of that quantity. Okay, see, uh, because when we write certain units, we do not make use of base quantities to write or to express the units every time, isn't it? For example, when I say, when I ask you to give me the unit of force, you say Newton. Yes, that is the right answer, but Newton, the unit Newton, has fundamental quantities or base quantities inside it, isn't it? Base units are inside it. And using those base units, this unit is made. So Newton is the unit which will not give us the direct idea how the quantity force is dependent on other base quantities, isn't it? But when I say velocity, the SI unit of velocity is meter per second. And that expression, that unit of velocity can actually give me the idea how the uh, velocity, the quantity velocity is dependent on base quantities length and time, because the units are meter and second, meter per second. But when I take the unit of force or work, there and all, it's all the fundamental quantities are not given directly, and hence we cannot, fundamental units are not mentioned in the unit of the force and work, so we cannot get the exact idea of dependence of the quantity on the base quantities, right? Dependence of the quantities, the force, work and all, on the base quantities using the units. So this, that is why we were in need of another way to see or to get the dependence of a quantity on base quantities directly. For that, we will make use of dimensions. Okay, that is the reason we are making use of dimensions. So when I say what are dimensions, dimensions involves, or dimensions are dimensions of a physical quantity. Okay, dimension is written for a physical quantity. Dimension of a physical quantity are, see, these are the powers we say, powers or exponents. Okay, powers or exponents to which the base quantities, to which the base quantities are raised are raised for what? To represent the given quantity. So this is dimension. The dimensions are basically numbers. They are the powers. Okay, powers means what we will keep in the powers. We will keep numbers, some numerical value. So they are the powers to which the base quantities are raised to represent the given quantity. So which base quantities are we making use here? We all know that there are seven base quantities or fundamental quantities, LMT, talc. Out of them, we are going to choose LMT here, okay, because they are the one which will occur again and again and again. So let me give you the idea of dimension using an example now. So dimension of length, okay, dimension of length is simply a square bracket including capital L inside it, okay. Similarly, dimension of mass is again a square bracket including including capital M inside it, and a square bracket including capital T inside it is the dimension of time. Okay, when I say the unit of time, we represent it using S, second. So for mass, unit of mass, we put kg. For the unit of length, we put meter, m. But LMT, L, capital L, okay, particularly we have to make use of capital L. Capital L in square bracket represent the dimension of length. Capital M in square bracket represents the dimension of mass. Similarly, time. Okay. So now these are the dimensions of individual quantities or base quantities itself. When I ask you to get the, and similarly, let me give you the idea of other quantities also. The dimension, see, length, mass, time, current is one more important. Or before current, we can write the dimension of temperature. The dimension of temperature is capital K in square bracket. Okay, so keep that in mind. These are very important. Dimension of length is capital L, mass is capital M, time is capital T. For temperature, it is capital K in square bracket, and for current, okay, for current it is capital A in square bracket. Okay, so how many of them got over? 5. 2 more left. For amount of substance, whose unit is mole, if you can remember, within square bracket we need to write MOL, okay, within square bracket MOL in small. So A for current, keep that in mind. Ampere is the unit, that's why capital A. And mole for amount of substance, and CD is the small d in square bracket is the dimension of luminous intensity. Okay, so these are the fundamental quantities: length, mass, time, temperature, amount of substance, current, and luminous intensity. Each of them has their own dimensions. So now we will make use of these dimensions of base quantities to express the dimensions of other quantities. It goes as such. So the first example that I'm going to take is dimension of velocity. See, when I write the expression of velocity, it is distance or displacement. Okay, displacement by time, right? Displacement is nothing but length. So length by time will give me the dimension of velocity. So how should I write that? So in the numerator I should put length. Okay, see, these are just the representation of quantities. We will not consider any numerical value here. 5 meter per second velocity. No, 10. We are not bothered about the numerical value. We are just worried about how the given quantity, okay, how on which base quantities are used to represent the velocity, okay, and that itself is called dimensional formula. We'll see about it, but this is how we write it. Let me give you the idea. Displacement or length in the numerator and one time in the denominator, right? So the dimension of time is capital T in square bracket. So capital L by capital T, right? And when I put them together, I can also write this as, this is also fine, we can keep it as such, but we generally make use of pars to represent pars, okay, which means, see, since it is only L, I can write that as L raised to 1, right? And then T comes to the numerator and becomes minus 1. So L1 T minus 1 is the dimension of velocity, okay? L1 T minus 1 is the dimension of velocity. So this is about velocity. In the same way, if I write the expression or the dimension for acceleration, so acceleration is change in velocity by time. So it is finally change in velocity means it's velocity itself, nothing else. Okay, dimensionally, the unit and dimension will be same for velocity and change in velocity. So in the numerator, it's somewhat like this: velocity by time, right? That is what is acceleration. What is the dimension of velocity? Dimension of velocity is here L1 T minus 1, and in the denominator we again have time. So dimension of acceleration is L1 T minus 2. Okay, and let me give you one more example. Force. Okay, see, force, we have an expression F is equal to ma, right? Mass into acceleration. And now we need to get the expression or dimensional formula of force. So for force, dimensional formula would be mass into acceleration. Dimension of mass is simply capital M. Dimension of acceleration is L T minus 2. Putting them together, it is going to be M1, or let me write the quantity length first. That's fine. In some references you find quantity mass first, okay. In some references you find L first, that's not a problem. So it is L1 M1 T minus 2, okay. So L1 M1 T minus 2 is the dimension of force. So we can say the quantity force has one dimension in length, one dimension in mass, and minus 2 dimensions in time. That is how we can say the dimension of force is as such. Clear? So when I say a quantity, it has three important things now. One is its numerical value, and then its unit, and then the dimension. Numerical value gives the amount of the value of the quantity, so how much the quantity is, how much it measured, and uh, the unit shows which quantity it is, isn't it? Without unit we cannot judge it if the quantity is not mentioned. And unit also helps us in the scale of the quantity, because 1 centimeter, 1 meter are different scales. And when I say dimensions, dimensions helps us in getting the dependence of the quantity on base quantities. So now we can get the quantity force is dependent on base quantities as such. Okay, so these are few examples for dimensions of different physical quantities. And in NCERT you will find a lot of dimensions given, You don't need to memorize all those dimensions, because by the end of the course we will be looking uh, various looking into various formulae. So each formula can give us the idea about the dimension of the quantity. Okay, each formula can give the idea about dimension of that particular quantity. So you don't need to bother about memorizing all the dimensions. No need to worry about that, because by the end you will have so many formulas, so many concepts, so many uh, definitions. All of them will help you in getting the dimensions of different quantities. Okay, so that is about different dimensions of different physical quantities. And now, uh, see, this these powers are the dimensions. Okay, these values 1, 1, minus 2 are the dimensions of force. And writing them like this in square bracket, this entire thing is the dimensional formula of force. Okay, so this is the expressing it in this way is the dimensional formula of force. So the expression which involves how and, okay, how means what are the powers, and which, okay, how and which base quantities are used to get the dimension of the given physical quantity. Okay, so the expression which has which shows the expression, this is the expression which shows how and which base quantities are used to get the dimension of given physical quantity. Okay, is called dimensional formula. Okay, dimensional formula, this itself is dimensional formula. It is showing us how and which quantities are used, because see, in force we have three dimensions used, three base dimensions used, and this temperature, current, mole, none of them are used here, isn't it? So how and which base quantities are used to represent uh, the dimension of given physical quantity, this expression is known as dimensional formula. And uh, the equation which equates the dimension of force, see, I can write that as such, within square bracket capital F. So this is quantitative dimension of force. If I simply write Cf, that is the actual quantity force, 5 Newton, 10 Newton, so on so. But when I keep that capital F in square bracket, that is the uh, dimension of force. Okay, so dimension of force equated with its base quantities. Okay, equated with its dimensional formula. Okay, dimension of given physical quantity equated with its dimensional formula is called dimensional equation. Okay, so all of them put together makes an equation, and which can be considered as dimensional equation. See, there are not much technical points there, but it's all about terminologies. You should keep them in mind. That's it. But you should concentrate more on how to express given physical quantity, how to express the dimensions of given physical quantity. You should make use of the expressions, the formulae, and using them you have to express the other quantities, dimensions as such. Okay, so this is about dimensions, dimensional formula, and dimensional equation. So this is how we do it. You should keep all those things in mind. Okay, yeah, right. There is a basic principle that uh, tells us that in an equation, when we equate or add or subtract two quantities, those two quantities must have the same unit, uh, or uh, not necessarily same unit, but the dimensions must be the same. Okay, let me give you an idea. See, uh, if I have two quantities. Say I have force and velocity as two quantities. 5 Newton of force and 3 meter per second of velocity. See, I can never equate them. Okay, I can never write 5 Newton is equal to 5 meter per second like that. No, I cannot do that. Basically, they are different quantities. They cannot be equated. At the same time, I cannot add them. Okay, so I cannot do 5 Newton plus 3 meter per second. No, this is wrong. So whenever we need to, that is because this force has different unit and this velocity has different unit. But when we take the same quantity, at the same time they're totally different quantities altogether. It is force, it is velocity, we cannot add them. So the basic rule that we're going to follow is, when we want to add or subtract or equate two quantities, those two quantities must have the same unit. They should be of same quantity. And when we equate, okay, basically it all comes to the level of dimensions now. So when we equate them, we can make use of the dimensions. Otherwise we cannot equate them also. So this principle of to add or to subtract or to equate two quantities, they must be the same quantities with same units. Okay, clear? When we add two quantities or subtract two quantities or equate two quantities, those quantities must have the same unit. When they have the same unit, obviously they will have the same dimension and same value, same, they belong to same quantity. And this principle is called principle of homogeneity. Okay, principle of homogeneity. Homogeneity. So using principle of homogeneity, now we are going to apply our knowledge of dimensions for different applications now. Okay, one of the use or application of dimensional analysis. What is dimensional analysis? Dimensional analysis simply equating the two quantities in numerator and denominator. I'm sorry, in LHS and RHS dimensionally. If the uh, the dimensions of quantities in RHS and LHS are not same, we say the, when we have done dimensional analysis, but it is not consistent, right? So dimensional analysis is just checking what is the dimension of this particular quantity and what is the dimension of this particular formula, and that's how, okay, we'll see uh, in detail, or we'll understand what is dimensional analysis through the applications itself. First application of dimension analysis is to convert from, okay, we are discussing about applications of dimensional analysis, applications or uses. Applications of dimensional analysis, to convert from one system of unit to other system of unit, we can convert from one system of unit to the other system of unit using dimension analysis. How do we do that? Yeah, we have I hope you all know about it, but again we are going to use dimensional analysis to do the process to convert from one system to the other system. We'll see how do we do that. So first let me take a simple quantity. Let's say velocity. What is the SI unit of velocity? SI unit of velocity is meter per second, right? And what is the unit of velocity in CGS system? So this is the unit of velocity in SI system. The same quantity velocity will have the unit centimeter per second in CGS system. So this is for in SI system, and this one centimeter per second is in CGS system. So if I have certain velocity, say 5 meter per second, and I want the expression, I want to express this velocity in centimeter per second, then how do I do that? Okay, I can make use of dimensional analysis to convert this much velocity, the 5 meter per second velocity, from SI system to CGS system as follows. So it is 5, right, meter per second in SI system, which is equal to, see, here I have one dimension of mass, right? I'm sorry, one dimension of length, meter, no, unit is meter, so it is one dimension of length, and minus one dimension of time, isn't it? So it is L t minus 1. Express the this is how we express the dimension of velocity. And similarly, when I write the value of velocity in centimeter per second, let me take that as some x meter per second, x meter per second, I'm sorry, x centimeter per second. It's in, so for CGS system, x centimeter per second. Okay, and here the dimension is simple L1 t minus 1, but what I'm going to take is, I'll take a subscript of 1 for meter per second, the SI system, and I'll take a subscript of 2 for this centimeter per second. I'll take this as, see, subscript, it's just the different way of expressing it. Okay, L1, L2, it's not the par is same, first length and the second length, right? T2 minus 1. First time, second time, their time altogether, the powers are same, L1 t minus 1. See, even when the units are changed, the dimensions of a physical quantity remains the same. Okay, that's the basic logic that we are going to make use of now. So many times we will not have the idea about centimeter per second or the particular particular formula, particular unit. Even then we can make use of dimensional analysis to get the conversion. So these two must be equal, which means we should have something like this: 5 L1 1 T1 minus 1 should be equal to x L2 1 T2 minus 1. So what we need is the value of x, right? So x becomes equal to 5 times L1 1 stays as such, T1 minus 1 stays, divided by L2 1 and T2 minus 1 in the denominator. So what is L1? L1 is the dimension of length in SI system, which is meter that we chose, right? So it is going to be, instead of L1, now I'll write meter. Okay, we could have directly done that, but we are making use of dimensions now. That's it. And T1 for time, it is seconds minus 1. Here L2 is centimeter because it's the dimension of length in CGS system. That's why I took L1, L2 differently. Okay, they are same length, dimension is same, but I have taken using different representation. That's it. So again, T2 S minus 1. So this S minus 1 cancels. Second is same for both of them, and the meter stays as such. And 1 meter, okay, let me convert meter itself. 1 meter is 100 centimeter, right? So in the denominator we simply have centimeter. So this centimeter cancels. We are again left with 100. So now we have x is equal to 5 times 100. Okay, x is equal to 5 times 100, because we started with 5 meter per second velocity, right? So 5 meter per second is also fine, and 5 into 100 centimeter per second is also the other way of expressing the same quantity, but in different unit, which is CGS system. So this is how we make use of uh, dimensional analysis to convert from one system of unit to the other system of unit. Okay, so this is for velocity with an example. Now we shall see two more examples, which are very important examples as of your board syllabus is concerned. We'll see them and understand how do we convert from one system to the other system. Right. First, we'll see the conversion for the quantity force. Okay, so for force, we all know that in SI system the unit is Newton. Okay, so the first conversion that we'll be doing from is from Newton to Newton is the SI unit in, excuse me, for force. Newton is the SI unit for force, and Dyne, D-Y-N-E, Dyne is the unit of force in CGS system. Okay, so now we are going to convert the unit of force from Newton to Dyne. Okay, so it is from capital N to dyn. Right, so see, I can write that as 1 Newton is equal to some n, small n, Dyne, because I don't know what is the conversion factor. If I get n, that itself is the conversion factor, and I can successfully convert from Newton to Dyne. So now my intention would be to get the value of this small n. 1 Newton is equal to n Dyne. So now what is the dimension of Newton? The unit Newton, dimension of force, which in turn the dimension of force. We all saw that the dimension of force was L1 m1 t minus 2, right? F is equal to ma. Yeah, L1 m1 t minus 2, and this is equal to n times dimension of Dyne is again L1 m1 t minus 2. Dimensions is same for both the units because they belong to same quantity, force. So since this is one set of dimension for SI unit, I'll write this them as L11 m11 t1 minus 2 because they belong to SI system. And since this belongs to these are again L1 m1 t minus 2, but since they belong to CGS system, I'll write them as L21 m21 t2 minus 2 for CGS system. Now what I need is this value of n. Okay, so this n becomes equal to, see, I can bring this L1 L2 m2 and t2 here to the denominator to the LHS, and they come to the denominator as follows. and then they become L1 by L2 whole to the power whole raised to 1, and M1 by M2 raised to 1, T1 by T2 raised to minus 2. What is L1? L1 is the dimension of force here, okay, the quantity of force. This is actually the dimension of length, okay, in SI system. So the dimension of length is L1, is taken as L1 for SI system, and in SI system it is the unit that we make use is meter. So instead of L1, I'll now write small m, meter. And instead of L2, what is L2? L2 is the dimension of length considered for CGS system. Okay, so dimension of length is L2 considered here. The unit of length in CGS system is centimeter, right? Whole raised to 1. And here M1 is the dimension chosen for mass in SI system, and M2 is the dimension chosen for mass in CGS system. So instead of M1, I can write kg here, because in SI system kg is the unit, and instead of M2 I can write simply g, gram, right, to the power of 1. And both in SI system and in CGS system the time unit is same, second, so they are going to remain same, is equal to n. Now let me bring the conversion factors. 1 meter, excuse me, we all know that 1 meter is 100 centimeter. Okay, I can write 100 as 10 to the power of 2, right? 10 to the power of 2 centimeter in the place of meter, divided by centimeter. And instead of kg, I can write 10 to the power of 3, because k itself is kilo, which is 10 to the power of 3 gram, divided by gram. G is equal to S by S. No conversion, because they are same units for time, is equal to n. So centimeter cancels now, gram and gram cancel, second and second cancels, and what we are left with is, see, so it is 10 to the power of 2 left here, and here we have 10 to the power of 3 left. From this, both s and s got cancelled, only 1 is left. 1 to the power of anything is 1 itself. So together it is 10 to the power of 2 into 10 to the power of 3, which is 10 to the power of 5, is equal to n. That's it. We have the conversion factor. So the conversion factor is 1 Newton is equal to, instead of n, I'll write 10 to the power of 5 Dyne. Okay. We have successfully converted the unit of force from SI system to CGS system. So this is how we convert from one system to the other system. So this question is the answer for, if they ask you like convert from Newton to Dyne, or 1 Newton to so and so Dyne, then this is the answer for that question. Important question. Okay. And now we shall see how to convert in the same way. The same procedure is followed to convert uh, from SI system to CGS system again, but the quantity will be different. Okay, the quantity will be energy or work. So we'll see how to convert the unit of work. Okay, what is the SI unit of work? It is joule, right? You all know that. So this time the question is to convert from joule to ergs. Okay, ergs is the unit of work in CGS system. Okay, Dyne was the unit of force in CGS system. Similarly, ergs is the unit of work in CGS system. So now we will see how to convert from joule to ergs using dimensional analysis. Before we go for the conversion, we should have the idea about dimension of work. Okay, so dimension of work or energy, both are fine. Okay, you can take any expression of energy that will give you the dimension and unit. Unit is not dimension of work and energy can be obtained. Okay, work and energy has the same dimension, same unit. So see, uh, let me take the expression of this kinetic energy. Okay, finally it's only energy which is required, which will give us the dimension. We are trying to obtain the dimension of work or energy, both are same, that's why. So kinetic energy expression is half mv squared, right? So what is m? M is mass of the object, so that will bring the dimension capital M. Okay, what is v? Okay, this is the dimension of small m, mass. What is v? V is velocity. Velocity has the dimension L1 t minus 1 whole squared. Okay, because it is v squared, that's why I should also square the dimension of velocity. So when I put them together, it is going to be L2 m1, because it's one, simply 1, t minus 2. Okay, L2 m1 t minus 2 is the dimension of kinetic energy, and hence dimension of energy, and hence dimension of work also. So L2 m1 t minus 2 is the dimension of energy and work. Keep that in mind. Okay, so we have derived the dimension of work and energy. Okay, L2 m1 t minus 2. So we are going to follow the same steps now. So it's 1 joule. We'll start with, as such, 1 joule is equal to some n ergs, because that's how we convert. 1 joule is equal to n ergs. So what is joule? The dimension of joule is just, we took that, we derived that, it is L2 m1 t minus 2. Since these dimensions belongs to SI unit, I'll keep L1 to m11 t1 minus 2. Okay, it is just representation. These values in the subscript will not have any numerical significance. It's only representation, is equal to n times. See, now the system is changed to CGS system, but the dimension will remain the same. Okay, keep that in mind. So change of system will not change the dimension. So it is going to be L2 1. Okay, I'll just change the subscript, rest is same. Sorry, not 1. L2 2 m2 1 t2 minus 2. See, the parts are same, 2 1 minus 2, 2 1 minus 2, only the subscripts are changed now. So now what I need is the value of n. So n becomes equal to, see, L1 by L2 raised to 2, m1 by m2 raised to 1, t1 by t2 raised to minus 2. L1 is the dimension of length taken in SI system. In SI system, the dimension of length is L1 that we choose. The unit of length is meter, because L1 belongs to SI system. L2 belongs to CGS system. So instead of L2, I should now write centimeter to the power of 2. M1 belongs to, again, the SI system, so which I can take as kg. M2 belongs to CGS, so I can take gram to the power of 1. T1 second, T2 is also second, because in both in CGS and SI the time has the same dimension, same unit second. So now the conversion starts. What is 1 meter equal to? 1 meter is 10 to the power of 2 centimeter. 100, no, 100 centimeter. I can write 100 as 10 to the power of 2 centimeter divided by centimeter to the power of 2, whole to the power of 2. This power should not be forgotten, very important. This should be carried. And here I have kg, so it is 10 to the power of 3 kg divided by, sorry, 1 kg is 10 to the power of 3 gram, 10 to the power of 3 gram divided by gram. And here the seconds will get cancelled. 1 to the power of anything is 1, so I can remove this part, I can neglect that. So it's 1 to the power of anything, no, that's why. And now here centimeter gets cancelled, gram and gram, because they are same now, both in unit, both units are same, so I can cancel them. Now what we are left with is 10 squared whole squared, isn't it? So this 10 squared is from the conversion. This whole squared is because the dimension of joule has a length raised to 2. That's the reason we have this 2 here. So n is equal to, this is n, 10 squared whole squared is 10 to the power of 4 into, from this what we are left with is 10 to the power of 3, right, into 10 to the power of 3. So altogether 10 to the power of 4 into 10 to the power of 3 is 10 to the power of 7. So now we have converted from joule to ergs. That's it. We needed the value of n. So I can write 1 joule is equal to 10 to the power of 7 ergs. This is how we convert from one system of unit to the other system of unit. So these are the standard questions. See, if you are fast enough, you can do this very easily, very quickly. Okay, there is no need of all these steps to get the final answer. But in board examination, we always expect you to write detailedly. So all the steps must be followed. Each step carries its own mark. So this conversion from Newton to Dyne, joule to ergs is asked in board examination, sometimes in 3 mark, sometimes in 5 mark. Okay, generally it is asked in 3 mark question. So if you just practice them once, they're very easy. These are the steps which has to be followed. Okay, these two are the standard questions. Apart from this, yes, there are possibilities of getting other conversions also, like velocity, acceleration, etc., etc. But this is the process. These are the steps which has to be followed for the conversions. Before that, you should have the idea about the dimension of the physical quantity given. See, in the beginning we did not have any idea about the dimension of energy or work. We derived it actually. After deriving it, we put that into this formula and continued the process. So whenever the dimension of a quantity is not given, ourselves should derive it and simplify to get the dimension. Okay, for example, one more example. Okay, this is done. So now I'll show you how to derive the dimension with one more example. Say I need the dimension of density. What I'll do, I'll go for the formula of density. Formula of density says rho is equal to m by v, mass by volume. So now, do I have the dimensional formula of mass? Yes, I do. It is simply capital M to the power of 1, m1, mass 1, no length, no time, only mass, no, that's why. What is the dimensional formula of volume? Dimensional formula of volume, see, volume is given by, you can take any formula of volume, volume formula of, say, volume of sphere, volume of cylinder, volume of cone, volume of cuboid, anything. So let me take the unit of formula for cuboid. So it is volume is equal to length into breadth into height. So when volume is equal to length into breadth into height, the dimension of volume, see, length, breadth, height are generally the quantities of length. They all belong to length itself, nothing else. Okay, we are measuring length. That's it. With different names. That's it. Breadth is also length. Height is also length. Okay, it's finally length, not mass, time, and all. So this length will have dimension of L. This breadth will also have the dimension of L. Height will have the dimension of L. So put together, volume will have the dimension of L3, isn't it? So the dimension of volume is L3. So now I can put that dimension here. So volume has the dimension L3. And now the dimension of density is M1 L minus 3, because L3 comes to the numerator, becomes minus 3. So the dimension of density is M1 L minus 3. See, in this example, we actually derived the dimension of two quantities. One is volume and the other is density. In the same way, I actually derived the dimensional formula for velocity also. Okay. So this is the process we will make use of, and in the same way we derived the dimensional formula of kinetic energy. So this is the process which has to be followed. We'll make use of the formula and get the dimension of that quantity. Okay. So that is about first application, and in the next session we'll see two more applications of dimensional analysis. Thank you.